In today's lesson, we're going to be looking at what is a derivative. Now, derivative is one of the main two topics in calculus. So let's see if we can define what a derivative is. The derivative of a function f at a number a is denoted by, here we have f prime of a. This is said f prime of a is defined as the limit of f of a plus h minus f of a all over h. Now this is what we've been studying for the last couple of weeks. We know that that represents the slope of the tangent line at x equals a. So a derivative f prime of a represents the slope of the tangent line at a, or we could say f prime of a represents the instantaneous rate of change of a function at a. We also found the slope of the tangent line using this formula. Now remember, we talked about this, that these two find the slope of the tangent line at a. It's just a different form. So this still represents f prime of a, which is the instantaneous rate of change of our function f at x equals a. Let's find the derivative of f of x, which is x squared minus 8x plus 9. The derivative is defined as f prime of x. And we know f prime of x equals the limit of f of a plus h minus f of a all divided by h as h approaches 0. That's the definition of a derivative. So it's asking us to find the derivative of f of x. That's what this represents, the derivative of our function f of x. Now notice for this one, it does not tell us to find the derivative at a particular point. So we're going to leave a in our formula. This equals the limit. Now we're going to plug this in. So a plus h gets plugged into our function. So every place we see an x in our function, we're going to plug in a plus h. So we'd have a plus h squared minus 8 times a plus h plus 9. So I just took the function and plugged in a plus h. Then it says minus f of a. This means I'm going to plug in a to our function. Now it says we need to subtract off this entire quantity. So I'm going to put a parenthesis there, or a bracket, so I don't forget to distribute my negative. So plugging in a to our function, we would get a squared minus 8a plus 9. And this is all divided by our h as h goes to 0. So there's our limit. And we know this limit finds the derivative of the function. Let's evaluate this limit. Now I want to clean this up a little bit, so I'm going to multiply a plus h squared. I'm going to multiply that out. That's a squared plus 2AH plus H squared. Then I'm going to distribute this negative 8. So we would get negative 8A minus 8H plus 9. Now we have to distribute the negative through the brackets, so we'd have minus A squared plus 8A minus 9. All divided by H as H goes to 0. We recognize we have some terms that we could cancel. A squared, negative A squared. We have a negative 8A, positive 8A. I see a positive 9 minus 9. So let's clean that up and see what we have left. We have 2AH plus H squared minus 8H divided by H as H goes to 0. Now if we tried direct substitution at this point, you see we would get 0 over 0, the indeterminate form. But we recognize that we could factor out an H. So we'd have 2A plus H minus 8, all divided by H as H goes to 0. And we can reduce the H's, and we're left with 2A plus H minus 8. Now we can use direct substitution. So if we substitute 0 in for H, we get 2A minus 8. There is the derivative, and this would be our f prime of A. So you can see my notation up here. I actually should write, since we are finding the derivative at A, this is our f prime of A. F prime of A represents the slope of the tangent line, or the instantaneous rate of this function at any value of A we choose. I believe we may need this for our next question, so I'm going to rewrite our results here. This is f prime of A. So let's erase some of this so we can get to the next part of this. And this should give us enough room. Find an equation of the tangent line to the parabola x squared minus 8x plus 9 at the point negative 2, 29. Now to find the equation of a tangent line, we need to find the slope of that line. So we need to find the slope at negative 2. Well, we can go back up to our derivative now, because we're looking for f prime of negative 2. That would give us the slope of the tangent line at x equals negative 2. So let's find out what that slope would be. We're going to plug negative 2 in for A. So we would get negative 4 minus 8, negative 12. That represents the slope of the tangent line when x equals negative 2. So the equation of the tangent line would be y equals negative 12x plus b. Now if you wanted to use the point slope form instead of the slope intercept form, that's fine. Now to find b, we could plug in negative 2 for x, and 29 for y. So we'd have 29 equals negative 12 times negative 2 plus b. And now we could solve for b. So when we solve for b, we'd have 29 equals 24 plus b, so we'd subtract 24 from both sides, and it appears that b would equal 5. So the equation of our tangent line in slope-intercept form would be y equals negative 12x plus 5. The position of a particle is given by the equation of motion. F of t equals 1 divided by 1 plus t, where t is measured in seconds and s in meters. Find the velocity and speed after 2 seconds. If we're trying to find the velocity of this particle, and we have the position function, f of t equals 1 divided by 1 plus t, the velocity can be found by taking the derivative of our position function. This would give us our velocity function. And since we're trying to find the velocity at 2 seconds, we're going to need to calculate this derivative, f prime of t. And we're going to use a again, so it would be f prime of a. So f prime of a, and we're going to go ahead and leave it as a and then plug 2 seconds in at the very end. You could find f prime of 2 at this point, and that would just give you the velocity at 2 seconds. But I'm going to leave this as a. We know f prime of a equals the limit of f of a plus h minus f of a all divided by h as h goes to 0. I will be plugging in a plus h into our equation wherever we see our variable. So we would have 1 divided by 1 plus a plus h now we have minus f of a, so minus, now let's plug in a wherever we see our variable, so we'd have 1 plus a divided by h as h goes to 0. At this point, if we tried direct substitution, we'd plug in 0 for h, and we'd have 1 divided by 1 plus a minus 1 divided by 1 plus a, which is 0, all divided by 0. We get the indeterminate form. Let's find a common denominator in the numerator. So if we found our common denominator, we'd get 1 plus a minus 1 plus a plus h divided by 1 plus a plus h times 1 plus a, all divided by h as h goes to 0. If we simplify, we would have the limit of 1 plus a minus 1 minus a minus h, all divided by 1 plus a plus h times 1 plus a, and I don't know if we're going to be able to squeeze in, divided by h as h goes to 0. The 1's cancel, the a's cancel, so we are left with the limit of negative h all divided by 1 plus a plus h times 1 plus a all divided by h. And I could write h in the denominator as h over 1. And now if we invert and multiply, we would have negative h times 1 plus a plus h times 1 plus a. And we can see that the h's reduce, and we are left with the limit of negative 1 all over 1 plus a plus h times 1 plus a. And now we can use direct substitution. As h goes to 0, we're going to plug in 0 for h. So we would get negative 1 divided by, if h goes to 0, we have 1 plus a times 1 plus a would be 1 plus a quantity squared. We are trying to find the velocity at 2 seconds. So we are trying to find f prime of 2. So we are going to plug 2 into our derivative to get 1 divided by 1 plus 2 squared, which would be negative 1. 1 plus 2, 3 squared is 9. So we'd get negative 1/9. And our units would be meters per second. That is the velocity of the particle at 2 seconds. Now, velocity, we know you have an associated sign with it. It can be positive or negative. That indicates the direction. Now, the relationship between speed and velocity is speed equals the absolute value of your velocity. So speed is always positive. So since we have the velocity is negative 1/9 meters per second, we would take the absolute value to get our speed, which would be 1/9 meters per second. And notice this would be positive because speed is always positive. A manufacturer produces bolts of fabric with fixed widths. The cost of producing X yards of fabric is C equals F of X dollars. What is the meaning of the derivative F prime of X, and what are the units? Now, if our function represents the cost of producing X yards of fabric, F prime of X would represent the rate of change of the cost of producing X yards of fabric. So the units would be dollars per yards. Part B, in practical terms, what does it mean to say that F prime of 1,000 equals 9? Well, the derivative represents rate of change. So this is the rate of change of cost. Now, what we're plugging in for right here into the derivative, that would represent yards of fabric. So what's the rate of change at that instant? What's the rate of change of cost for producing 1,000 yards of fabric? And we would see our cost would be increasing at $9 per yard at that instant. Which do you think is greater, F prime of 50 or F prime of 500? So if you think about what's going on with that, we're producing more fabric at F prime of 500 compared to F prime of 50. So what happens to our cost as we are producing more and more yards of fabric? Well, what can happen is that the more fabric that we are producing, the less the costs may be increasing. We are able to distribute more of our costs over more of the fabric. So if we only produce 1 yard of fabric, we have a lot of costs to spread out over that 1 yard of fabric. Whereas if we're producing more, we have more yards of fabric to spread out our costs. So F prime of 500 would probably be lower than F prime of 50. Now, when we're looking at F prime of 5,000, we may have to expand our, operation, and there's going to be more costs associated. So we may see our costs rising when we produce that much more fabric. So the rate of change of F prime of 5,000 greater than the F prime of 500. It's important to just be able to interpret the difference between, if I would have asked what simply is F of, let me go back, if I would have asked what is the difference between F of 50 and F prime of 50. It's very important to know the difference between F of 50 and F prime of 50. F of 50 is just finding the cost of producing 50 yards of fabric, where F prime of 50 is finding the rate of change of cost exactly when we have produced 50 yards of fabric. Let PFT be the population of the United States at time t. The following table gives approximate values of this function by providing mid-year populations. Estimates from 1988 to 1996. Interpret and estimate the value of P prime of 1992. And again, make sure that you understand the difference between, if I asked you P of 1992, well, that's asking you for the population at 1992, which is in our table, 255 million. But P prime of 1992 is asking for the rate of change of the population in 1992, mid-year 1992. What is the rate of change of the population? This one's asking us to interpret and estimate the value of P prime. Now, when we're given discrete values, we know that if we're trying to find the rate of change in 1992, we're going to take 1992 to 1990 and create the secant line and find the slope of that secant line. Then we'll take 1994, 1992, create the secant line between those 2 points, and then average them. So for on the interval from 1990 to 1992, we would be looking at 255,000,000 minus 249,440,000 divided by 1992 minus 1990. That would give us 5,562,000 divided by 2, which is 2,781,000. If we found the slope of the secant line from 1994 to 1992, we would have 260,292,000 minus our 255,002,000 divided by 1994 minus 1992. And here we would get 5,290,000, then divided by 2 is 2,645,000. Now we said we are going to take those and average those two. So if we took 2,781,000 plus our 2,645,000 divided by 2, we would get 2,713,000, which represents our instantaneous rate of change for the year 1992. So think about what that means. We know the population. If we said P of 1992, we would say, well, that's 255,002,000. But we're trying to answer the question, what is P prime of 1992? The rate of change of the population. We're saying the rate of change of the population is 2,713,000 in the year 1992. And if you look back at the numbers and say, does this make sense? You can see from 1990 to 1992, there's a rate of change over those 2 years of about, 249 to 255. So there was approximately 5.5 million, and our rate of change is about 2.7 million per year. So you can see that's reasonable. The last concept that we're going to be looking at is how to graph a derivative function just by looking at the function of a graph. Here we're given the graph of f of x, and it's asking us, well, can you graph the derivative of f of x by plotting some points. Keep in mind that the derivative represents the slope of a tangent line at a particular point. So for instance, if I wanted to find a point on the derivative function for x equals 1, I would have to estimate the slope of the tangent line at that point. So if I can find the slope of that line, that is the point I would plot at x equals 1 for the derivative graph. Now, just estimating the slope of that line, I would say if I'm going down 1, I'm going over maybe, let's see, a quarter. So I can see the slope of that line is negative. And if I just estimated that slope and plotted a point, say I thought the slope of the line was negative 1/4 or negative 1, whatever I think it is, I'm going to plot the point for x equals 1 for the derivative graph that equals the slope of that tangent line. Now let's take a look at some pretty obvious points that may help us. If I wanted to find the slope of the tangent line at this point, notice the slope of the tangent line at that point would be 0. So I know on my derivative graph it has to go through that point. And I can see another point where the slope of the tangent line would equal 0. So for this value of x, I can see the tangent line again would be 0. So I know the derivative graph has to go through that point right there. Now, let's analyze a few more points. Let's look at x equals negative 1. What I do know about the slope of this tangent line is it is positive. I can see the slope of that line is positive. So if I were to plot a point on the derivative graph at x equals negative 1, I would need to estimate the slope of this tangent line. And if I was very careful and I extended that tangent line, I could then maybe calculate the slope of that line. If I'm going up 5, I've gone over maybe 1/4. So the slope of that line is pretty steep. So let's say I did estimate that I'm looking at this. I'm looking at this line and trying to estimate the slope. So I would be going, if I'm looking at 2 points on this tangent line, I would have one here and maybe one here. So I'm looking at, if I go up this much, I have to go over this much to be back on that tangent line. Well, this distance from here to here is 5. And the distance that I moved in the x direction, I'm going to estimate that because each one of these yellow lines is approximately negative 1/2. And so I went about halfway, so 1/4. So I'd have 0.25. So the slope of that line would be the change in y divided by the change in x. So the change in y is 5 all over the change in x, which is 1/4. So I would say the slope of my tangent line is 20. So when x equals negative 1, I would plot a point way up here at 20. Let's choose another point. just to estimate the slope of the tangent line. Let's say I chose -1/2 and drew in my tangent line here. Now, compared to when x is -1, what can you tell me about the slope of the tangent of this line compared to the slope of this line? Well, you should say the slope of the line at -1/2, this one here, is greater than the slope of the line at -1/2. I may have said that backwards. The slope of the line at x equals -1 is greater than the slope of the line at -1/2. So we know the point for the derivative graph would be less than 20. And if we estimated that slope, we would probably get something maybe down in here. Now, what happens to the slope of the tangent lines as we're getting closer and closer and closer to this value here, x equals 1/2? Well, we know that is getting less than, say, 5. So it's approaching this value down here at 0. So if I was to draw the derivative graph through those points, what I have so far, I may have something like this. After this point right here, where the slope of the tangent line was 0, we can see the slope of the tangent lines now are negative. So I know this tangent graph is going to go down into the negative area. And I'm just going to look at the graph and say, it looks like the slope of the tangent line is most negative right in this area, because when I get over here, I can see the slope of the tangent line is going back towards 0. So if I estimated the slope of this tangent line here, and I said that was, let's say, 10, I would put a point here, and I would say that's where this graph has the slope of a tangent line that is most negative. Because like we said, these tangent lines now, you can see, are going back up towards 0. And we know we have to go through that point there. Now, after the slope of the tangent line here, we can see the slope of the tangent lines as x moves towards 4, as x moves towards 4.5, they're getting very positive. So we would anticipate the derivative graph would have this shape. So the idea behind drawing the derivative graph to a function is you have to analyze the slope of the tangent lines for values of x and then plot those points at that x value. And a good technique is to identify any values of x, like we did here, where the slope of the tangent line would be 0. We knew it was 0 there, and we saw the slope of the tangent line here was 0, so we plotted a point here. And then you can analyze the graph here. I know the slope of the tangent lines are going to be positive. So I know I'm going to be in the positive area up here, and then we're going to be approaching 0. And after this 0, the slope of the tangent lines become negative. That's why our derivative graph went down into the negative area. And I identified where the graph looks like it would be, the slope of the tangent lines would be most negative. And then the slope of the tangent lines started to get closer and closer to 0, so we know we had to come back up here. And then we said the slope of the tangent lines is x equals 3.5, 4, 5, 6, 7. They're getting very positive, so it would be above the x-axis, so we moved in this direction. So this does take a little bit of practice, but you analyze the slope of the tangent lines to plot the points for the derivative graph. So if I made a table of values, I would be looking at my x values, and then I would be looking at the slope of the line. So for instance, we said when x equals -1, we estimated the slope to be 20. When x is 1/4. So here's where x is 1/4. We said the slope of the tangent line were 0. So that would be a point on our graph. So we could plot these points and then draw our derivative graph through those points.